So good morning. So we are in the last part of our vehicle dynamics course, and we have just started understanding the various construction details and types of tires in the last class. Especially those are called pneumatic tires. So we also have looked at various coordinate axis system that are considered to describe the forces and moments that are generated at the tire road interaction, and that is what is called the tire axis system by SAE recommended axis system. So we are going to look at in today's first part of the lecture, one of the important force that is developed at the interaction is what is called a rolling resistance force. And then we are going to look at a primary force for traction of a vehicle is what is called a tractive force. So how it has been generated, some basic theory of them is what today's class we are going to learn. So I'm just going to share my screen. So hope this screen is visible to you, my ITInspire board. And this is lecture number 43. Today's date is 8/12/2021. So in today's class, we are going to understand an important force, what is called the rolling resistance force. So rolling resistance force is not going to aid your forward motion of your vehicle. It is the resistance for the forward motion of the vehicle. And this would be always present in your rolling tire. That's why it is called a rolling resistance. How is it being manifested? How this force is generated at the tire road interaction is what let us first understand. So if you look at the tire rotation, it can be a free rolling tire, or it can be a tire rolling due to driving torque, right? So rolling due to driving torque, that means it's an accelerating tire, and then rolling down. Rolling down instead that is slowing down is a better word. Slowing down, that means it is decelerating due to braking torque. Braking torque. So what do you mean by this is that you need to understand what is the condition of free rolling tire. A free rolling tire is the one where it is not subjected to driving torque, neither braking torque. So it is rolling because of its initial disturbance or initial push it has been given to the tire, that you could say. For example, a gentle slope, no, it is not very high slope. It is not coming down the hill slope. It is a gentle slope. You see your vehicle is stopped and then you don't put your handbrake. Then what is happening? Your vehicle is rolling down back. So that's what is, you can imagine that is a situation where you do not have neither braking torque or driving torque given. So if it is complete perfect level road, no slope, then it can be. But even someone touches the vehicle, you can see that it would be moving if it is not engaged with any of the gear. It is a neutral gear and no brake is handbrake is applied. That you can look at it. So that rolling is what is free rolling. So during free rolling, if you look at the free body diagram of the tire, so as there is a load acting on the tire and it is inflated tire, you have a contact of tire wheel assembly with the road with some contact patch. So this is the contact patch. And see, this vehicle is under free rolling condition. That means I don't apply, this is omega, it's rolling. but it's rolling without application of wheel torque, driving torque, or it's not stopping by braking torque. It's rolling. It's a free rolling condition. So you would have some linear velocity of the wheel center here. At that time, if you look at the distribution of normal pressure here, generally is not symmetry, it is skewed. So if I just draw a vertical line through this center of the contact patch, and my free body diagram, the weight of the load that comes on the wheel is vertically acting down, and the load that is supported or balanced is because of this normal pressure in the contact patch into the area of contact patch is what is the resultant force that is acting. That won't be in this line, that would be slightly in this forward direction. So in reality, in practical case, the free rolling tire would have its normal pressure in the front half of the contact patch more than that of the rear contact patch as it start rolling. If it is not rolling, it is stationary and you are loading it, the contact patch you can see that is uniformly distributed. At that time, this offset won't be there in the forward direction, and rather it would be balancing this weight. So as it start rolling freely, you see this comes forward, and now what is happening? This would create, so this is your FZ. So this FZ would create an unbalanced couple here. So there is a couple present here, and that couple to be balanced during for the dynamic equilibrium. The balancing force is what is that comes here is by manifestation of a rolling resistance force, RR. So this RR would be acting in this. So RR into this distance would be creating a moment, and that moment couple is what is balancing Fz into this distance, and this force is what is called the rolling resistance force. And you see this couple is clockwise couple, the rotation is counterclockwise. So this couple. Hello. So someone is please mute your. Yeah, thank you. So here you could see this rolling resistance force manifesting to balance this couple. And what is this couple Fz in this offset distance? It's a clockwise couple or clockwise moment about this, and that is against the rotational moment of your movement of this. So that is called rolling resistance moment, and the rolling resistance moment to be balanced for its dynamic equilibrium even at free rolling condition. So this force RA is manifested there. So this is rolling resistance force, and this rolling resistance force is directly proportional to this load that is acting on this, and the proportionality constant is what we are defining as rolling resistance coefficient. So if you look at here, this rolling resistance is primarily depends upon the loading or the material of the tire. That's very important. So the loading is what is, so this is free rolling condition. When I apply a driving torque, it is loaded tire. When I apply braking, then it is loaded tire. So the scenario of braking or scenario of driving, we will see in the next part of the lecture. And that would be the necessary understanding required for to develop the theory or understand the theory which is developed by Julian, which is one of the earliest theory for to understand the generation of these forces in the contact patch, tractive or braking effort in the contact patch. So at the moment, free rolling condition is helping you to understand this rolling resistance force. Then you may ask the question, what would happen to this rolling resistance force? Will it disappear in driving or no? It is getting there. This forces will be always there, whether it is in rolling condition or in driving torque applied or braking. Why? Because it is an inherent property. It's because of the dissipation of energy due to tire deflection, the tread deflection during its rolling action. So the tread deflection during rolling action is what is making this non-uniform distribution of this normal pressure, and that normal pressure resulting force and the corresponding couple is what is rolling resistance couple, and that is balanced by this force. So this is some basic theory behind what is how this rolling resistance force that comes into play, right? That is why you have seen that the rolling resistance force is accounted in our free body diagram of the whole vehicle when we consider the tire rod interaction point along with the tractive force consideration, along with the braking force consideration. So this is inevitable. And if you take free rolling condition, it is the only force would be there in a longitudinal direction during the drive, right? Yes. So now this is because of the hysteresis of the tire material due to deflection of the carcass while rolling. So what is that basic mechanism of this is due to hysteresis that present in the tire material. So tire material subjected to compression as well as tension during rolling. So when I apply the driving torque, the carcass getting compressed. That is in front of the contact patch and the part of the contact patch which is adhered to the ground getting compressed, and that compression would be changing when I apply deceleration or when I apply braking. At that time, what would happen? That is going to be stretching. So this kind of cyclic loading is what we call it as hysteresis that is present in the tire material, and this deformation of the tread is responsible for energy dissipation, as the tire material maximum is of viscoelastic nature material. And that viscoelasticity nature is what is responsible for this hysteresis present in the tire material, and the deflection during the of the carcass during rolling is what is responsible for this all understanding that we had now. So that is going to be the primary cause of rolling resistance, right? So primary cause of rolling resistance. Now what I mean by that, if the rolling resistance of 100%, if I have that force, so 90% 90 to 95% is because of hysteresis. So this because of this 90 to 95% is because of this phenomena alone. So the remaining 10% would be because of the secondary influence. The secondary influences are the friction between your tire and the road contact. What I mean by friction? So friction here is this is as it is going to roll. You would understand in the second part of lecture. It is not going to have completely adhering to the ground. So the leading part would be having adhering to the ground, and the trailing part would start sliding, and that is that reason why you can also there is this skew of this distribution of this. So that sliding zone would progress gradually towards the leading end. So there is a sliding part of this contact patch, and that is what is going to be dictated by the friction between these interactions. That is also be responsible, and that is going to be maybe around 2 to 10% of the total rolling resistance contribution, and remaining up to 1.5 to 3% of that is because of the circulation of an air trapped inside this tire wheel assembly, because it is compressed air is filled inside the cavity of the tire wheel assembly, and that circulation of the tire during that circulation of the air during the rolling motion, and also the surrounding air circulation of the tire wheel assembly is what is responsible for contributing this much. So in this also, if you look at the hysteresis loss from the tire is concerned, its component or its parts are very important. So out of this, if you look at almost 75% of this. So if you look at this proportion again, 75% of this 90% to 95% is because of tread and tread material. So the tread material rubber compound is different than that of the sidewall, all we have seen in the last class. So this would cause 75% of this. And then if you look at carefully, 13% is coming from sidewall and its material compound. Sidewall is subjected to corresponding shear. Similarly, you also have this shear, longitudinal direction. You have a shear deformation of the tread as well as in, the sidewall shear deformations. So that is what is going to be of 13% contribution. And again, if you look at some 12% contribution that comes from shoulder region. Shoulder region is the one which connects your tread and the sidewall. So if you look at the profile, it goes like this, right, for the tire. So this is the portion tread, and this portion is sidewall, and this portion is which connects is what is shoulder region, right? So this is tread, this is shoulder region, and this is sidewall region. So these are that contribution that comes from that, and you have here the beads. So the bead is going to contribute maybe by 2% of the rolling resistance. So of this 90%. So what is the primary source of rolling resistance is this hysteresis of tire material and the tread and sidewall deflection during rolling action is what is responsible, right? And you can also look at, we are going to look at some of the case study and these factors. These are the factors that affect rolling resistance. That first factor is this tire construction and material, which is what we discussed now. And of course, the road surface condition do have an influence on this rolling resistance. And then the inflation pressure, speed, temperature, whether the tire is subjected to traction or braking, the dimension of the tire, all are important. The researchers have done a study on this, having varying these parameters, these factors, and looking at the variation in the rolling resistance, and that is quantified through the rolling resistance coefficient here, what we have. So that's what we are going to look at quickly in upcoming slides, and then we get into the second part of lecture. So look at here. So the rolling resistance coefficient, looking from this automotive handbook, you can see that it would be different for passenger car as well as truck tires on different road surfaces. So if it is a concrete asphalt road, look at this value. Generally for a passenger car is this. On the other hand, if you look at for the truck tires, it is smaller than that of passenger cars. And you can look at on a field, that means it is not a highway or the road surface. If you get into an agricultural field of the road, you see the rolling resistance do play vital role. So that total load, 10% of the load being taken by this. So we know your traction Fx is limited by Vp times W. So you see in that the rolling resistance alone is going to have 10% of your W. Right, that's what is that minimum here if it is on the off-road. Whereas if the same on the asphalt road, it is just a single 1%. So see the difference of this rolling resistance and the tire, right? So these are the values just given, and you need to have this idea of what are this rolling resistance coefficient and how much compared to that of the expected tractive or braking force, the rolling resistance do contribute to understand. And see here the rated load and inflation pressure, how these tire types or the construction of tire do get affected. You can see in this graph, you can also have its influence over the speed. So that speed is on horizontal axis, and you have one vertical axis, rolling resistance coefficient. And you see that radial tires and bias tires. So you have this result clearly says the radial tire almost have got a constant value here, and it's a smaller rolling resistance coefficient compared to the bias tire. So if you should say car tires, if it is a radial tires, I have less rolling resistance. And the influence of this on a rolling resistance less pronounced as an increase of speed compared to that of bias ply tire. See, in a bias ply tire, it is more than radial tire, this coefficient. Also, it is going to, it shows that there is a gradual increase of this coefficient as the speed of your vehicle increases. The similar trend that could be there for your truck tire as well. In a radial tire, it is also seen in a truck case, there is an increase. And the influence of speed is more in truck tires compared to that of a passenger car tire. So this is how you should understand this influence of speed and the types of tire construction, radial tire and bias tire. So radial tire is less rolling resistance tire is the conclusion in this slide. And then road surface influence, if you look at, there are different textures that define the road surface. So you have here an example, 6 road surfaces are there. Polished concrete till and asphalt with coarse seal coat road surfaces, right? So that has been classified based on the texture of the road, where the texture can be of macro texture or micro texture, and it is going to be defining the smoothness of the tire, the road surface, or harshness of the road surface. We'll see that already we have seen, and I explain you what is this in the next slide and come back to this slide once again. So if you look at the road surface texture is defined by this 2 scale, micro texture scale, vertical scale, macro texture scale, horizontal scale. So in both the scale, if you go up, it is referring the increase in roughness of the road. If you go down from this origin, it represents the smoothness of the road surface with the micro texture scale. In the similar way, if you are coming on a positive right side, your roughness increases. So positive quadrant in this represent the roughness more. On the other hand, if you go to the third quadrant, it is the smoothness. So third quadrant road surface is the perfect flat surface. There is no undulation at all. Whereas on the other hand, you see this undulation is more on this first quadrant. Now, how does this other 2 quadrants are defined? So if I have my road surface here appearing is of macro smooth, because on this side, and micro rough road surface. So macro smooth and micro rough road surface are proper blend of your bituminous with the aggregates, that stones, and then it is binded nicely, and this is the road, and you have this undulation randomized, but it is not so high as that of this. So this is a general asphalt road surface texture. So asphalt road surface texture is combination of macro smooth and micro rough road surface, right? So here if you look at this peak to peak would be of some few mm to few micrometers to few mm's, whereas in this case it would be of in centimeters, one peak to the other peak. So that is because of it is micro rough surface and macro. Macro means the aggregates are bigger aggregates. Micro roughness is referring to the density of this binding material there. And you see here it is a macro rough and micro smooth road surface. So what does that mean is that the surface bituminous all are binded nicely, but you see the protrusion of these aggregates are up. So that's responsible, and that is what is this way. So it is kind of a wavy road, whereas there is no finite aggregates, those blended nicely. So the bigger aggregates were there, the stones were there in this. So this is how road texture has been described. Based on this understanding of texture, if you look at again these 6 road surfaces from polished concrete till rolled asphalt, and then asphalt with coarse seal coat. If you look at compare the road, for example, to a new concrete road. So it is a smooth macro texture and micro harshness road. So in this, if you look at, you have some undulation. It's not very smooth, and it is taken as a reference now in this comparison. So if it is 100% here, is what is the relative rolling resistance of new concrete with respect to that. If it is 100%, you look at that the polished concrete would have a lesser rolling resistance. It is only 88% of that of the reference road surface. Whereas on the other hand, the last road, that seal coated asphalt road, has got 33% more than that of this in this rolling resistance. So the surface of the road surface and the texture do have an influence on your rolling resistance. So this is coming from again another case study reported by the researcher. And then if you look at rated load and inflation pressure influence, you see here the rated load is 100% if you consider. The inflation pressure is 165 kilopascal, And you can say that the pressures are alphabets representing A, B, C, D. These inclined lines are the pressure lines, and the upward inclined lines are the curves are the loading. So if I have to take the rated load and the rated inflation pressure is this. In all the graph you can look at. So this plot for the radial tire, on the other hand, you see for bias ply tire you have this. So this graph here, what do I have is for this rated load and this. So now with respect to this, you can see that what is the variation of your loading resistance. So if I increase my load, what is happening? It is increasing in rolling resistance. If I increase my pressure, what is happening? So the pressure here is increases, the rolling resistance decreases. See, interestingly, so B is what is 165. So 220 kilopascal is given by C. So the rolling resistance is decreases as the inflation pressure is increases on the dry asphalt road. So this is on a dry road surface, hard dry road surface, hard dry road surface, right? So if I decrease my inflation pressure, then my rolling resistance forces increases. That means that more the contact patch, and no, you would have the offset distance will be more in the lower inflation pressure. Right. On the other hand, if you increase the load also, you see it is increases, because if you have more load and more inflation pressure, that's going to have more contact patch area, and that's going to put your resultant of normal load offset distance more. Obviously, there is more rolling resistance moment, and to manifest to balance that, the increase in rolling resistance that will come, and that has been quantified by means of rolling resistance coefficient here. So in this case, it is not put an explicitly rolling resistance coefficient. How do you get that? You divide this on y-axis, what is there, by the load, and you get the value, right? So this is that a comparative study is being made on different types of tire construction, tires, radial tire and bias tire, and you can witness that bias tire has got more rolling resistance influence on these conditions compared to that of radial tire. And bias belted tire is the combination of both, and that has got an intermediate one, right? So this is that influence of your load and inflation pressure on rolling resistance. And continuing with that, if you look at the threshold value of speed of the tire failure is to be understood, and that you can witness here, this tire is rolling now clockwise with omega. So its forward direction is this, so if it is on a flat surface, but it is now on the drum. Is on this drum. So you can see that as I increase the speed of this, you see that contact patch which is coming out has got a permanent deformation, and there is a waveform, and that waveform is what is called the standing waveform, and that is going to be permanently appearing here. The more this deflection, the more the dissipation, the energy loss, and that is going to result again in more of rolling resistance. So there is a critical speed. At that speed, if you look at, you would also have material to develop a crack, and then crack propagation and failure of the tire would lead into that. So that speed is what is dictated for the tire before it has been sent to the OEMs. So that every tire samples are tested, and they are coming out of this, and that is how they go in for rating of this speed rating. We have seen in the last class on the chart. So that has been given by this equation under the radical circumferential tension in the tire divided by density of tire material per unit area, right? So this is something that you should be aware how the speed rating of the tire is brought in to say. And continuing with that, looking at the influence of tire temperature. So tire temperature, when I say it is not an ambient temperature, it is the surface or the tire temperature. What is that it is having? And it can be of internal tire temperature, that's called. And you see this tire temperature as it is increases. So this all lines, incline positive slope lines, are referring to the temperatures. So this is a temperature of 40 degree centigrade tire surface temperature, and the speeds are this. So you have the speed here 80 to 50 kilometers per hour, like that. So this is 80 kilometers per hour speed. So this line is referring to speed, and this is, And this analogous way, how did you look at the rated pressure and load? You can look at it here. So as the temperature increases, you have your rolling resistance coefficient decreases, and the speed increases, your rolling resistance coefficient increases, right? And if you look at again the temperature, the shoulder region alone, which is given primary important because that's going to have more flexing action, because that's connect to your tread and the sidewall, and that portion is very important in contributing. This, and of course you have looked at the shoulder region contribute lesser than that of tread and sidewall, but we can't neglect it. And the region, shoulder region dissipation is primarily influenced by the temperature. And you see here, as the temperature increases in the shoulder region, your rolling resistance comes. So at the hot sun, summer time, if trucks are on the road surface, they would experience lesser rolling resistance, right? Contribution from the shoulder region of the tire. So these are all something that you should be aware of when you talk on rolling resistance. So we have understood in this first part of lecture what is rolling resistance force, how is it being manifested. It's because of to balance the rolling resistance moment about your y-axis of the SAE coordinate system, and the influence of rolling resistance primarily because of the hysteresis in tire material and the other influencing parameters, and that we have witnessed through these case study results. So that's lecture number 43. You have any doubts on this topic, you can ask. Otherwise, I'll just stop this recording. I'm going for a fresh recording of the next part.